what do we need? This is already what I talked a little bit when I was explaining neural networks. But for our neural network to be reverse engineered, at least we need the information about the layers, what kind of layers, or what is the number of layers, what is the number of neurons, what are the activation functions, what are the weights. So let's try to decompose this into different smaller parts of the attack, and basically the algorithm. Yes, so we will be reverse engineering the full algorithm. So machine learning model is an algorithm. Exactly. So we will decompose this what do we need into 4 parts, and first we will attack each part separately. Just are we talking feed-forward networks or also convolutional networks? So convolutional networks are also feed-forward networks. So here we are talking about feed-forward networks, specifically multi-layer perceptrons and convolutional neural networks, but they are both feed-forward. About activation functions, we assumed, yes, not only that we assumed they were only the known ones, but we also assumed they were only the known and popular ones. You could do much more, but it did not make sense. There is also quite a lot of known activation functions. So I think maybe 30. Well, TANH, ReLU, sigmoid, softmax, CeLU, so many options today, especially with deep learning. Everything is very popular. But actually, when you are looking at the real-world implementations, there is quite a limited number of activation functions that is commonly used. So yes, if someone would be using something that is completely unknown, so completely unknown activation function, that would be quite difficult then to break, simply because it would go kind of in the same direction of obscurity of the settings. So we could always recognize some patterns that the activation function follows, but we would need to invest quite a lot of effort to be able to reverse engineer it. So aiming for the known ones is easy, because you will see we will do the timing approach. Aiming for the unknown ones, it would be doable, but would be quite more work to do. But commonly in those networks that are used in bigger settings, you rarely see custom activation functions. People do use those activation functions that work quite well. So what is activation function? It's a function defining the output of a node given input or set of inputs. So here you can see the formula. So you have our weights, something also that we need to reverse engineer, combined with the input plus some bias, not important. We sum all this and we transform it in certain kind of way by using the activation function. And common activation functions are, like someone said, unfortunately, I do not know how to read the names, but common ones are sigmoid, TANH, ReLU, and of course softmax. Sigmoid, TANH, ReLU is what you will commonly see in the inner layers of your neural network, so hidden layers. Softmax is what you will see at the last layer, because softmax is what will give you probabilities. So from there, you will go to classification process. Softmax is able to tell you, well, this looks to be having weight 0, this looks to be having weight 1, and so on, so on. So that's why softmax is also very important. And actually, already from here, you can see the expressions, the equations for those functions to be very different. Well, for the first and second, kind of similar, but already third, fourth one. Yes, so we measure, the question is, did we measure before the attack how much each activation function costs? Well, not before the attack. Let's say during the attack, so we have the implementation, we have our own implementation, and then on that implementation, we are able to measure the behavior, and then use that kind of information to recognize the pattern. Yes, in that sense, it's offline measurement, because activation function has the complexity of depending on the input, of course, but we will see that the patterns are very different. So here you can already recognize if we would be aiming for time-wise, we would expect here to be very different behavior. Do you agree? So which one do you think would be the simplest to attack? Well, the simplest to run, sorry, not to attack. The fastest to finish. Well, yes, exactly. That, because you can already see this equation is much simpler than the other equations, and we could expect this to be much faster. And indeed, when we would looking at times, you could look at the minimum time, maximum time, mean time. But let's go into graphical depiction, and here is how it looks like. So you can see first ReLU, then sigmoid, then tan H, and then softmax. You can recognize very, very different timing behavior. So already from this will enable us to recognize what kind of activation function do we use. What is interesting to note is that sigmoid and tan H do have some similarities. So you could see the pattern is kind of similar. It's left, right, well, let's say symmetrical in that kind of sense between those two. But actually what differs is, yes, of course, the shape. Yes, they look the same, so you would expect that, of course. And I'm saying this because later we will just be seeing that actually this is kind of even the most difficult part to attack. But what is not really visible from the graphs is that the magnitude on the y-axis is quite different. So the values here are quite different. So even though the shapes are kind of similar, their magnitudes are quite different. Cool. So we covered the first part. So depending on the timing behavior, we can assume what kind of activation function is used in a single layer. So in a single layer, it's not all layers, one layer. Now let's see how can we get the weights. And this is probably the coolest part of the attack. So to recover the weight of every neuron, we will use our CPA, so our correlation power analysis. What do we attack? Well, we will target the multiplication. So going a couple of slides back, here we see we multiply the weight with the input. So this is what we aim to attack. You assume the weight sampled from Gaussian normalization. Yes, so first, we do not need to assume that, although most of modern neural networks would actually use the random initialization, so one of the popular random initializations. But for us we just need to assume that that we attack the Xavier or her or whatever Gaussian, or there are many popular initialization techniques. What's important for us is that it's just multiplication. So we have multiplication is equal to our input times the weight. And remember, we said we know the inputs. Okay, so we just need to guess the weight. So how do we do that? Well, first we already said we will use our Hemingway model, and we will correlate the activity of the predicted output for all hypotheses of the weights. So remember the slide when I gave the loop all key hypotheses. Here we need to have all weights hypotheses. So this is already telling you the more precise we are in the weight decision, the more hypotheses we need to cover. So that's why, for instance, here we said we will limit our attention to 2 decimal places. Okay, so we will be carrying only up to 2 decimal places just to be limited with the number of weight hypotheses we need to test. So what do? Well, we'll compute for all hypotheses of the weight W, what is the Pearson correlation coefficient from our side channel measurement. And then whenever we have the correct value of the weight, it will result in a higher correlation, and it will kind of stand out from all the wrong correlations. let's just discuss how to do that, and then you will see from the graph that it really looks like that. So first, how do we do that attacking guessing of all possible weights? So since we are working with microcontrollers, we set floating points, and we know how compiler will handle floating point operations. So it's enough that we consider IEEE 754 compatible representation, and then since this is 8-bit microcontroller, you know the representation will have 32-bit pattern, so there will be 4 registers, and those 4 registers will have sign bit, exponent bits, mantissa bits. So this is how you would represent your floating point value by IEEE standard. And then we just target the multiplication of known input with unknown weight. For every input, we assume all possible options for the weight. We do the multiplication, we recover the mantissa, we recover the sign exponent separately. And this is how it looks like. So on the y-axis, you can see the correlation, and black line is the correct guess or the targeted value, while the red line is incorrect value. So you can see actually that when our weight guess is correct, we have the higher correlation than for the wrong values. And this is on the left side for the first byte, on the right-hand side for the second byte. And of course, you will do the same for the third byte and so on and so on. Not important. But this is the point. We know the input, we check every possible weight, and for the correct weight, we will have better correlation value. The same process you will be using for your traditional side channel attacks, for instance, for AES. You will try all possible keys. You know the inputs. For the one that you get the best correlation, you will say, well, this is my key guess. So the only difference here is we are not interested in key hypothesis, we are interested in weight hypothesis. And then this is the second part. So we managed to get the first part. We know the activation function, we know the weights, and do not be fooled. There is a lot of effort. This is on the level of every neuron of every layer. So you need to do a lot of experiments, and you need to recover the weight for every neuron separately. But it's doable. It's not even so much time to do that. With modern processors, actually, it's very fast. Now, what is left? It's left to reverse engineer what's the number of layers and what's the number of neurons per layer. And once we have that, to combine all that in a nice picture. So first, to obtain the big network structure, we can use simple power analysis, what you already discussed. Here, we just call it SEMA because it's based on EM analysis. And you can see 3 different pictures, and you can recognize patterns. At this point, forget about red lines. The red lines are here just to make our life simpler. So just look at the patterns. So in the first one, you could recognize 1 pattern, 2 patterns, 3, 4, 5, 6 repeating. This is the same principle how you were recognizing square and multiply operations before. Here, again, you can recognize 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You cannot recognize why the red line is here. So no problem there. I completely agree with you. I said 2 hidden layers, but on the basis of this picture, I can recognize there are 11 neurons, but I do not know is it 1 layer, 2 layers, or 10 layers. So this is what we cannot recognize from this. And the same goes for the third picture. So again, we recognize some patterns, but again, we do not really know how to recognize where is the boundary between the layers. So what we are able to do with simple power analysis, we are able to basically count the neurons. Okay? So now the only part that is left is how do we find the distinction between layers? Anyone have idea how to do that? How, for instance, I show you the second picture. How would you find that here is the boundary between the layers. So boundary means, think of neural network as having input, having a couple of hidden layers, and having output. Okay, so how would I know at what point starts a hidden layer? So let's say I have let me just explain. Let's say we have two layers, two hidden layers. So we have our input, one hidden layer, second hidden layer, output. Okay, so how would I know where is the boundary between the first hidden layer and the second hidden layer? Option is compare different window sizes. Well, yes, but again, what is a window? Since we do not know where the layer starts or stops, we do not know what a window would mean. So Sagi says depends on the activation, maybe. Yes. Activation could help, but think of it in the big picture. We do not know how to do. We cannot do the attack part per part. I just show you how every part how can be done, but on the big picture, to know where to even test for the activation function, I need to know that is the layer end. So although I showed you the activation function first, you first need to know where is the layer boundary, and then at that point you measure the timing. Okay, people are typing. Let's see. I'm curious. If the activation is simple, there will be drop at voltage. Yes, maybe. It's complicated the opposite. So yes, so feed-forward network. How can this help? Very good hint. But let me just explain why. Well, drop at voltage. So regardless, is it drop or voltage or spike of voltage, we still do not know that this is the end of a layer or something happening in a layer. So yes, if we would have the assumption that whenever we see a spike, that means it's a stop of a layer, great, you could use that. But in essence, we cannot work with that assumption because let's say we do not measure that kind of behavior. So we do not see some kind of drop that can be really easily distinguishable. Yes, so activation function will have some pattern, but that will not be enough to distinguish. So let me also give you the computation for the first layer ends before the second layer computation starts. Excellent. That is, I do not know, sorry, I cannot understand the name, but this is very good observation. Exactly. The computation for the first layer will end before it stop for the second layer. Wait, the max mean delta of the amplitude is different with layers have a different numbers of neurons. Yes, that's completely true, but since I do not know how many neurons is in a layer, because I do not know where is the stop of the layer, I cannot say anything about max mean delta. Because if I knew this is my last neuron of a layer, I would already have the answer question. I would say, well, this is my end of the layer. But since I do not know where is the end, I do not know how many neurons are there in that layer. I just know the full number of neurons. So think of this, what Elior said, computation for the first layer ends before the second layer computation starts. And think, how could you use correlation power analysis to use that kind of information? So the answer to break this is to use CPA, correlation power, or CMI, so correlation EM analysis. How would you use it? Think about hypothesis. hypothesis. What kind of hypothesis would you need to give that would be able to give you a hint into direction? Is the first layer end, or is the second layer begun? What kind of hypothesis would you need to take? Typing. Okay, I will continue simply because that we are not late, but I kind of hope some of you are in the right direction. You will just need to think a little bit more about it. And I completely agree, this is not so trivial to see. Once I will tell you, you will say, yes, it's trivial, but to get to this, it's not so easy. So what you do? Well, you know that a neuron belongs to a layer. And if you start with the beginning of your neural network, you kind of assume a neuron will belong either to the first layer or to the second layer, because there is nothing else. It cannot belong to 77th layer because you are just at the beginning of your neural network. And then you will have two assumptions. First, you will assume that a neuron belongs to the first layer. Second, you will assume that the neuron belongs to the second layer. So what do we do? Well, we will start by targeting the first hidden layer, and then from the first continue. And we will have the input, so it's a vector of length n0. And so the input x can be represented by x1 all the way to xn0. And then we have our two hypotheses.